Hi guys, in today's video I'm going to look at the Sainsmart Genmitsu 3018-MX3. This is a 3-axis mini CNC supplied in kit form. It can mill and engrave several different types of material, which I'll be testing later in the video. This is what you get in the kit. The frame is made from 2020 and 2040 aluminium extrusion along with phenolic resin plates. The X and Y axis are driven by 8mm lead screws and NEMA 17 stepper motors. Support is provided by rods and linear bearings, and the table is one piece of aluminium with an area of 300 by 180mm. The Z-axis assembly is a 3D printed unit supplied pre-assembled, and it's also driven by a NEMA 17 stepper motor. The spindle motor is a 775 type operating at 24 volts DC with a specified no load speed of approximately 7,000 RPM. The stepper motors and the spindle motor are controlled by a controller PCB. This is designed to be used with Mach 3, which is a commercial software package. There are connections for the stepper motors, spindle motor, USB connection to a computer, power, and an MPG socket for a handheld pendant. There are also connections for an emergency stop switch, a probe for automatic Z-axis height setting, and limit switches. Limit switches are installed on all 3 axes, and they are connected to the control circuit via optocouplers. The stepper motor drivers also make use of optocouplers. The drive current for each stepper motor is preset, but it can be changed by connecting a voltmeter to the test points and changing the potentiometer setting. The final set of connections on the PCB are for a laser module, which is not supplied. The power supply is a brick type with a C8 figure of 8 input connector. It's suitable for 110 or 240 volts input, and it has a 24 volt 5 amp output. Parts in the hardware kit are labelled and referenced in the instruction manual, which is very good. There's also a mini CD with copies of the instructions and software. Moving on to the build, using a washer as a spacer, the blue couplers are fitted onto the stepper motor shafts and secured by tightening the grub screws. A stepper motor is screwed to the right hand X-axis side plate. Then a limit switch is fitted, along with 2 wire holders. A limit switch is also fitted to the left hand X-axis side plate, to the front Y-axis base plate, and the back Y-axis base plate. The base frame is constructed by bolting the front and back plates to the 2 lengths of 2040 aluminium profile. Then the linear bearings are slid onto the rails, and the rails bolted to the front and back plates. The anti-backlash mechanism is assembled onto the lead screw. Which is then inserted into the frame through the bearing. The second stepper motor is attached to the back plate. The lead screw is inserted into the coupler and secured with the grub screws. The frame bolts are then tightened. Making sure the frame is square. T-nuts and bolts are loosely installed in the linear bearing mounts. Then the aluminium table is placed on the bench, and the T-nuts slid into the slots. The table is centered and the bolts tightened. The mechanism is checked for smooth operation, and the limit switches are also checked. Next, the left and right side plates are mounted to the base frame using T-nuts and bolts. The T-nuts insert into the track and lock when they're turned. The X-axis guide rails are inserted into the linear bearings in the Z-axis carriage assembly, and then the guide rails are bolted to the side plates. Two lengths of 2020 aluminium profile are inserted between the side plates and bolted into position. The X-axis anti-backlash mechanism is assembled and screwed into the Z-axis carriage assembly. The lead screw is attached to the stepper motor. The side plates are adjusted, and then all of the bolts are tightened. The spindle motor is installed in the Z-axis carriage assembly. The controller PCB is bolted onto the matching acrylic plate using spacers and T-nuts. And then installed onto the back of the frame. T-nuts and bolts are installed on the acrylic side plates, and then they're attached to the frame. Next, the limit switches are wired to the control PCB, starting with the X, then the Y, and then the Z. Some additional cable holders are screwed to the frame, then the stepper motors are wired to the control PCB. First the X-axis, then the Y-axis, and then the Z-axis. Finally, the spindle motor is connected. This is a good point to test that everything is working okay before final cable management. Finally, the power supply is plugged in, along with the USB cable. The power switch is turned on. The collet is fitted into the collet holder. One of the supplied engraving bits is installed. And you can visually check that the bit is properly centered. Moving on to the software, the kit comes with a mini CD which includes a trial copy of Mach 3. Mach 3 is an application which controls the CNC machine and sends G-code to it. It's highly configurable and has lots of features. The trial version is limited to 500 lines of G-code, which is just enough to test out the software, but to do anything more you'll need to buy a software license. An alternative is Drupal CNC. This is simpler than Mach 3, but it works well and it has a higher G-code line limit. So first let's install Mach 3. There's no need for the parallel port driver. Once Mach 3 is installed, a couple of files should be copied from the CD into the Mach 3 directory. Firstly, the Mach 3 mil file, and then the BL USB Mac-V32 DLL file. Now we can run Mac 3. Select the reset button. The tab key brings up the virtual pendant, and now we can check that the axes are moving correctly. They're all moving backwards, so to change that we go into the config menu, ports and pins, motor outputs tab, and change the dia low active entries for the X, Y, Z axis. Hit reset and then the tab key again, and the axes are now moving correctly. Next, let's have a look at homing and soft limits. Homing is a way of consistently setting the machine coordinates to a known 0 position by using the limit switches, and soft limits prevent the machine axis moving past their physical limits and causing damage. The configuration can be found under the config menu and then homing / limits. Under home neg we set the directions that the axis should move to find the limit switches. For the Z-axis, the top position will be set to 0 and the bottom position will be a negative number. For the X-axis, the left-hand side will be 0 and the right-hand side a positive number. And for the Y-axis, the front will be 0 and the back will be a positive number. The soft limits are configured under soft min and soft max. For the X and Y axes, the soft max values are chosen to just prevent the X and Y limit switches being activated. And for the Z-axis, the soft min value is chosen to just prevent the Z-axis limit switch being activated. Once that's configured, select Ref or Home to initiate the homing cycle. The kit also comes with a touch plate whose function is to automatically set the tool height. It is connected to the probe and ground connections on the controller. The crocodile clip is connected to the bit and the touch plate is placed on top of the milling surface. Once the auto tool 0 function is initiated, the Z-axis moves down until the bit and the touch plate make electrical contact. It then deducts the depth of the touch plate and sets this as the Z-axis 0 position. First measure the depth of the touch plate. Then to configure the Auto Tool 0 button, select the Operator menu and Edit button script. Select the Auto Tool 0 button, delete the existing script. Next we need to copy a script from the CD. This can be found in the Z-axis Automatic Tool Setting folder. Open the Z-axis Auto Tool 0 code file, copy the contents, and paste that into the script editor. Enter the touch plate depth, and then save. The Auto Tool 0 button will then initiate a probe cycle. Next we need some CAD software to turn our designs into G-code. There is lots of choice, but two good free options are Carbide Create, which is a standalone application that you can download from the Carbide 3D website, and Easel, which is an online browser-based application that you can find on the Inventables website. So let's have a go at creating something using Easel. To access it, you just need to sign up and log in, and then you'll be presented with a blank project screen. First select the measurement units. Then under the machine menu, we can enter the size of the CNC work area, which is 265 by 165 millimeters. Next we select the material type, which is aluminium, with dimensions of 200 by 150 millimeters and a thickness of 1.2 millimeters. The milling bit is 1.2 millimeters in diameter. Then we select the custom cut settings, and I'm going to start with conservative values of 80 millimeters per minute feed rate, 50 millimeters per minute plunge rate, and 0.1 millimeters per pass. Next, select a rectangular shape, set its outline to cut outside, and the cut depth to 1.2 millimeters so that it cuts all the way through. The option for holding tabs is enabled. These are used to hold the shape in place when you're cutting all the way through the material. The length, height and quantity can be specified, and the position on the shape. By selecting the Shape tab, we can specify the size of the rectangle, radius the corners, and set its position. Next, let's create some text. Select a font, resize and position the text, enter 0.5mm for the cut depth, and then select an outside outline. Next, we're going to create some mounting holes. Select the circle shape, enter a cut depth of 1.2mm, turn off the tabs, set the diameter to 3mm, and the position. We can copy and paste the second circle, and then change its position. Give the project a name, and finally generate the G-code by selecting Machine, Advanced, Generate G-code, and Export G-code. Next, the aluminium sheet is mounted on the wasteboard using painter's tape and CA mitre adhesive. This is a very simple and effective mounting method, much better than double-sided tape. The tape is applied to the material and the wasteboard. Activator is sprayed on the material side, and the adhesive applied to the wasteboard side. The material is positioned, and as soon as they're pressed together it forms a very strong bond. Next, the machine is homed and the machine coordinates set to 0 by pressing the Ref All Home button. The jog keys are used to move the end mill to the bottom left corner of the material, and the 0, X and Y buttons are pressed. Then the touch plate is used to 0 the Z axis by connecting the crocodile clip to the end mill and pressing the Auto Tool 0 button. The G-code is loaded into Mach 3 by selecting File, Load G-code. The Go to Z button sends the end mill to the 0 position, and then the end mill is raised to a safe height with the jog keys. To start milling, press Cycle Start. The lubricant that I've used here is CT90 cutting fluid. Milling aluminium is quite a messy process and the little chips get everywhere. Once finished, the aluminium is levered off the spoil board, and then it's quite easy to remove the tape. I have also tried cutting a front panel out of 3.1mm or 1/8 of an inch plywood. The feed rate is a bit quicker this time, and the drill hole feature of easel was used to create the mounting holes. This uses the milling bit in a similar way to a drill bit. This is a little sign that I made from 3mm thick clear acrylic sheet. I used cast acrylic rather than extruded acrylic as it has a higher melting temperature and it mills easily. If you use extruded acrylic, then you'll probably find that it melts on the bit. To mount the acrylic sign, I made a stand out of 18mm or 3/4 of an inch thick MDF. I used a 3mm end mill to rough out the shape, and then a 1.5mm end mill for the detail. There's also a small rectangular section for the base. So that's what you can do with the Genmitsu 3018-MX3 mini CNC. Hope you found the video useful. Thanks for watching and see you again next time.